hopefully you can all see this. Okay, hello everyone, and thank you so much for attending my talk on concurrent incorrectness separation logic. I'm Azalea Raad, and this is joint work with Josh Berdine, Derek Dreyer, and Peter Hearn.
Hold on 1 second, Azalea. I'm sorry, we don't have volume in the room just yet. So
okay.
What do you want to do? Please.
Tell me when to resume.
Okay, speak now.
Okay, so in a nutshell,
yes,
concurrent incorrectness separation logic, or Sizzle for short, is the first work to extend the theory of incorrectness separation logic with concurrency as a formal foundation for concurrent bug detection and analysis. So let's start with a quick overview of what incorrectness logics are in general. Incorrectness logic, the very original work of Peter Hearn, and its later extension, incorrectness separation logic, are both formalisms that can be used for proving the presence of bugs, i.e. for bug catching. This is in contrast to traditional for logics where we use them for proving the absence of bugs, i.e. for verification. Incorrectness logic and incorrectness separation logic are both under-approximate forms of reasoning, meaning that we can write triples of the form that you can see on the screen that say that every post state S in Q can be reached by running program C on some pre-state S prime in the set P. In other words, Q is included in the set of reachable states, and that is to say that Q under-approximates the set of reachable states. Pictorially, if the set of reachable states, the post is given by this outer black oval, then we can think of Q as this smaller inner oval that is included inside the set of reachable states. And this is good news because it means that every bug that we identify as part of Q is by definition is going to be in the set of reachable states, i.e. it's a reachable bug, it's a true positive, it's a real bug. Of course, that this comes at the cost of missing some other bugs that are reachable but are not inside Q, but this is okay because our number one priority is to reduce noise, and that is to say to reduce false positives, meaning that we absolutely want to avoid raising an alarm and reporting something to developers as a bug, whereas as a matter of fact, it's not a bug. Now, incorrectness separation logic is a later extension of this work of incorrectness logic with exactly the same reasoning principles and interpretation, except that it additionally buys us compositionality, specifically in terms of the code analyzed and the resources accessed by a piece of code. So it inherits the canonical frame rule of separation logic that says that, okay, if you can prove a triple about program C, let's say if you detected a bug in program C, then you can actually extend that to all other resources by adding additional resources, meaning that you could also find that bug when you run program C on bigger states, where you have extended both the pre and the post states by additional resources denoted by this R here. Oh, I don't know what happened, just a sec. Something went very, very awry. 1 second. So hopefully you can see this now again. Okay. Now, so the problem here is that the incorrectness logic and incorrectness separation logic are both great for, as a formalism for detecting bugs, but their number one caveat is that they don't support concurrent programs. On the other hand, when we turn to the state of the art for bug detection tools for concurrency, there has been a recent trend on developing tools based on under-approximation. There is the RaceD tool for race detection at Meta, as well as a recent tool for deadlock detection at Meta, both of which are based on under-approximation. And remember, we said that for bug detection, our number one priority is to reduce noise, to eliminate false positives. And as a result, each one of these tools have formalized their analysis and established a no false positives theorem independently to say that their bugs are real. The problem here is that because there is no unifying underlying theory for concurrent bug detection, each one of these analysis tools had to go and formalize their analysis and prove this no false positives theorem independently. And ideally, we would like to do this in one unifying framework. And this is exactly where Sizzle enters the picture, concurrent incorrectness separation logic, as a unifying framework for concurrent bug detection. So when we started exploring the design space for Sizzle, there were many decisions to be made, and for inspiration, we turned to the verification world, for the concurrent separation logic world, for the over-approximate analog. And we soon realized that, of course, lots of decisions and lots of design choices to be made, and which is actually very nicely captured by this graph of Ilya Sergey that has documented the genealogy of concurrent separation logics in the correctness world. And this messy picture was actually identified as a problem by Matt Parkinson in his paper called The Next 700 concurrent separation logics. And in it, he argues that we shouldn't have to invent a new logic every time we want to reason about a new flavor of concurrent program. Instead, we should have a unifying framework, a parametric framework, which can instantiate different verification techniques in. And this is what led into the views framework and the general views framework later on. So similarly, we wanted to avoid the same pitfall and avoid being responsible for the next 700 concurrent incorrectness separation logics. And this is where we took inspiration from the views framework, this general framework, and designed Sizzle as a general parametric framework that can be instantiated for different use cases and different bug catching scenarios. Specifically, Sizzle is, as I said, the first unifying framework for concurrent under-approximate reasoning. It's general and it can be instantiated for different use cases. Specifically in the paper, we have used it for detecting memory safety errors, instantiated for memory safety errors such as null pointer exceptions, news after free errors, for data races, for deadlocks, and as well as other examples. Now, Sizzle is sound. We have proved its soundness, and by definition, remember the definition, the soundness of an under-approximate framework means that there are no false positives. So, as a result, we guarantee that any instance built within Sizzle is also going to inherit this no false positives property, which is great. And by extension, any tool built on top of the Sizzle instances will get this no false positives property for free. In fact, in the paper, we argue that the formalism that we use in our Sizzle RD instance, our instance for race detection, is very much analogous to the way the RaceD handler detects data races, and similarly for deadlock detection. Now, next, I want to show you an example of how we use Sizzle for bug detection. But before I do that, I need to show you two tiny technical points and then move on to an example. So the first is very simple in that when we actually write incorrectness triples, there's one additional component that I've been hiding so far, namely this exit condition denoted by epsilon, which can either be OK to denote a normal execution or error for an erroneous execution. So this exit condition tells you how this final state in Q are reached under normal executions or erroneous executions. For instance, for a simple program of skip, the states are unchanged and it's always reachable under a normal execution. Skip never errors, whereas the explicit error statement always ends up in an error state under the erroneous exit condition. And of course, again, it doesn't change the state. The second thing I want to talk to you about before showing an example is the different classes of bugs that we have identified when working with Sizzle and how we can go about designing thread local and compositional analysis around these different classes of bugs. So the first class of bugs is what we call local bugs. And as the name suggests, these are bugs that are due to one thread. So a simple example of this is what you can see on the screen now, where I have two threads. The left thread deallocates location X and then writes to X. And the right thread, I don't care what it's doing, it's running some program C. And you can see that regardless of what this thread in the environment, what this C is doing, there is a use after free bug at line L here, because I am trying to access X after it has been deallocated. So this is why it's local, because whether or not this will always be a bug regardless of what C is doing. Now, how do we go about designing thread local compositional analysis for this class of local bugs? Well, it turns out because this is the simplest kind of bug to detect because the bug is due to one thread, and as a result, we can use any existing sequential tool out of the box to detect such bugs. For instance, in the case of memory safety bugs, we can take the PulseX tool at Meta, which is actually based on incorrectness separation logic, and detect such local memory safety bugs. And this is because of one simple reasoning principle in Sizzle that I have that you can see on the screen now, that says if you have a concurrent program, C1 in parallel with C2, and you analyze C1 in isolation and you detect an error in it, then you can generalize this to the overall program. So if one thread errors, the entire program errors. And this is what we call the short circuit in semantics of error. So as soon as one thread encounters an error, the entire program terminates in an erroneous state. And it's because of this that we can just pick, in the case of local bugs, focus on one thread and analyze that. The next class of bugs, the next two classes of bugs are what we call global bugs. And again, as the name should suggest to you, these are due to two or more threads, and they occur under certain intermediates. So and we have further classified these to two subcategories, the first one being global data agnostic bugs, where threads do not affect each other's control flow. So here's an example. I have two threads, they're both trying to deallocate X. So you can see here I will have an error at either line L or L prime, depending on the interleaving I take. For instance, if I execute line L first, then I'll get a use after free error at line L prime and vice versa. And you can also see that there is no way these threads are affecting each other's control flow. They're not communicating with each other. And at all times, they will execute the deallocation regardless of what the other thread is doing. Another sophisticated example is the second one on the right, where the left thread is deallocating X and then writing to Z, and the right thread is reading from Z, and then non-deterministically writing to X. So this non-determinism is captured by this star operator that says non-deterministically decide whether or not you're executing this branch. Now, in interleavings, for instance, that where the right thread is executed entirely after the left thread, we can see that there is a use after free error again at line L because we are accessing it after it has been deallocated. But once again, the threads do not affect each other's control flow. For instance, in the case of the right thread, there are two execution paths, right? One in which we take the if branch and one in which we don't. But this decision is no way controlled and affected by the left thread because it's triggered non-deterministically and the left thread has no control over it. The counterpart of this data agnostic bugs is what we call data dependent bugs, where threads do affect each other's control flow. And to give you an example, we can simply adapt this top example here by replacing this non-deterministic condition with a concrete condition that says only execute the if branch if you read 1 from Z, i.e. when A is 1. And in this case, again, of course, we have a use after free error at line L potentially, but this time the left thread can affect the control flow of the right thread. Specifically, this thread only takes the if branch when it reads 1 from Z, i.e. when it reads the value written by the left thread. So there's some thread communication going on. So this distinction matters specifically when it comes to designing thread local analysis. So the question now is, as with the local bugs, how do we go about designing thread local analysis tools for these two categories of bugs? Specifically here, we have two conflicting desiderata, right? We have short circuits in semantics. So when we look at one error and it encounters one thread and encounters an error, the whole program terminates in an erroneous state. Whereas now we want to reason about threads in isolation, but the bug is due to two or more threads. So how can we do that? So the answer to that is a neat trick that we have come up with, where we encode errors as OK specifications to avoid this short circuit in semantics. And then we use the standard parallel composition rule of separation logic, which you can see here, which also is valid inside Sizzle, that says if you have a parallel program, C1 parallel C2, then you can go and analyze each thread in isolation, i.e. thread locally, derive some specification for them, and then combine them together by combining the pre and post using the star operator. And this is this is exactly how we deal with these data agnostic bugs. We encode them as OK specifications and do a thread local analysis. And now you might wonder, okay, this data agnosticism, how realistic an assumption is it? How can we assume that threads do not affect each other's control flow? Well, it turns out that's actually in practice assumed by a lot of scalable tools. And this is one of the ways they afford scalability. For instance, the RaceD tool and the deadlock detection tool at Meta both assume this data agnosticism. And I will show you an example of how we do this, for instance, for data races in just a minute inside Sizzle. Now, for the last category of bugs, even though for the data-dependent bugs, even though it's possible within the Sizzle theory to detect them, as of yet, there's no analysis tool that looks into this specific class of data-dependent bugs. So for the rest of the talk, I'm going to focus on data-agnostic bugs only and show you how we can detect them in Sizzle. There we go. Okay. So like I said, I want to show you data agnostic bugs in Sizzle and how we would go about detecting them. And I'm going to do that through a specific Sizzle instance we call Sizzle RD, Sizzle for race detection. And so to get started, let's first remind ourselves of the definition of a data race. So we say two memory accesses, i.e. two reads and writes, let's call them A and B, race with each other if two conditions hold. First, they must be conflicting accesses, meaning that they are by distinct threads on the same location, and at least one of them is a write. And we should be able to construct an interleaving, also known as history in the literature, where these two conflicting accesses appear next to each other. So to give you an example, here I have a program, two threads. You can see that they're both writing to location X. Now the right thread is writing to X while holding the lock L, the mutex L, whereas the left thread is doing so after having acquired the lock and released it. So you can see that I can construct a history by, let's say, or an interleaving by acquiring the lock and releasing the lock, lines 1 and 2, then acquiring the lock again at line 4, then executing lines 3 and 5. And you can see this witness history, this witness interleaving actually puts these two conflicting accesses next to each other, giving me the witness history that shows my data race. And intuitively, the problem here is that the location X is a shared resource, and to avoid races, it should have been protected by some mutex, for instance. So this left thread should have actually accessed X inside the lock block, and it hasn't. So in the example where I move the access within the lock block, then I no longer have a data race, and I can't construct a witness history because of the mutual exclusion semantics of lock X. So the question now is, how do we detect such races, for instance, in this simple example on the left, using Sizzle RD? Remember, we are assuming data agnosticism, and we're going to use the parallel composition rule of Sizzle, which is at the bottom here. And we're going to take a very simple approach. Remember, we want thread local analysis. So what I'm going to do, I'm going to look at each thread in isolation, construct a sequential history of each one of them, and then at the end, I'm going to analyze them to see if there are any data races. So unsurprisingly, I'm calling the left thread tab 1, the right thread tab 2, and unsurprisingly, at the beginning, they have an empty history. They haven't made any accesses, or they haven't taken any actions yet. Then using the parallel composition rule, I split up these resources, each one get their own history, and then I go about my sequential construction of the histories. So let's take the left thread. It acquires the lock, so in doing so, it will extend its history by just a corresponding lock event. So this now says, thread tab 1 has now made a lock access or acquired the lock on location L. And this is simply given by the Sizzle RD axiom that says, if thread tab, its history is so far given by H, then after acquiring the lock, you extend its history with the lock access, provided that the resulting history is well-formed. And well-formedness very simply says that the history should respect the lock semantics. So you acquire a lock only if it's not been already acquired, so you can't acquire a lock twice. And a thread releases a lock if it has previously acquired it. So you don't go about releasing locks arbitrarily. And in this case is, of course, the case. Similarly, we called unlock, and we once again extend the history with an unlock event, which has a very similar axiom, once again, appending an unlock event at the end of the history. And surprise, surprise, after we make a write access to location X, we once again extend the history by recording a write event. So here we have a write event W by thread tab 1 on location X at line 3. So I'm recording the line numbers because later on I will use them to pinpoint the exact location of the race. So unsurprisingly, the read and write accesses have the following axioms where we append the corresponding event, a read or a write, to the end of the history. So you can see I record the thread ID, the line number, and the location, but I'm not recording the values read or written. And this is because I'm in the data agnostic world where threads are not communicating with each other. The control flow is not affected by the values read or written. So as a result, these values don't have any bearing on the presence of the race. So I'll do the same thing for the right thread now. Acquire the lock, add a lock event, write access, a write event, and a non-lock and non-lock event. So now, again, using the par rule, I will gather these resources together. I'll compose them. And now the second step, which is detecting a race given the two histories. So analyzing them for finding races. So this is where a race predicate comes in and says that, okay, if you have these two sequential histories of two threads, tau 1 and tau 2, you can infer that there is a race between lines L1 and L2 witnessed by history H, if and only if the following hold. So first of all, you should be able to break up each one of the sequential histories like so, where you have a prefix and an axis A, another prefix and an axis B, where the axes B, A and B are conflicting according to the definition we saw earlier. And then for you to construct a witness history, you take these two prefixes of sequential prefixes and take a permutation of them, H prime, and that your witness history will be given by that permutation of the prefixes plus the conflicting axes at the end. Remember, I had to find a history where these two conflicting axes appear next to each other, and this is exactly what I'm doing. And finally, your witness history, of course, has to be well-formed, meaning that it has to respect the lock semantics. So back to my example, I have the conflicting accesses between lines 3 and 5 here, the two writes, and I have prefixes, lock, unlock, and lock. So what I'm going to do, I'm going to take the simple permutation where I concatenate the two prefixes together. So lock, unlock for thread 1. Sorry, here, yes, and then lock by thread 2, and then the two conflicting accesses. And this is how I have detected my race now. I have the race predicate that says lines 3 and 5 race together. Now, this may seem simple, but this is in fact very effective in practice. This is exactly the approach that RacerD takes to detect data races. So hopefully I have given you a convincing overview of Sizzle, and this brings me to the end of my talk. Just to conclude, to remind you that Sizzle is the first work to adapt under-approximate reasoning for concurrent bug detection. It's general in that it can be instantiated for multiple bug catching scenarios. It is sound, it guarantees no false positives for free in a sense. And of course, there is a lot more to be done in the future in terms of looking into data-dependent bugs in more depth and devising thread local analysis tools around them. And of course, other things such as mechanization and so forth. And that's all I have to say. And thank you very much for listening. So let me stop sharing. That's better. And here I am. Okay.
All right. Thank you. Yes. Are there questions from the audience?
Mm-hmm. Hey, thank you. Great talk. So I was wondering, does your tool do any analysis of branching or control flow constructs, or does it treat them all as purely non-deterministic?
So just to
and
say
if it
that
does treat them all as purely non-deterministic, how is there a difference between data-dependent and data-agnostic bugs in the first place?
Okay, so first to say that in this work is purely theoretical. We don't have a tool. We have the formalism, and then we have related it to existing tools such as RacerD and the deadlock detection tool. And in those tools, I can still answer your question in the context of those tools. They assume that all conditions are non-deterministic. So, and they don't do any, as of yet, those tools don't do any branching analysis. Now, one of the possibilities...
Sorry, Azalea, we couldn't hear the beginning of your answer. Could you start this answer again?
Okay, yes, sure. So just to say that the work that I presented, Sizzle is just a theoretical framework. We haven't, as part of this work, we haven't developed any new tools. What I've done is relate Sizzle to existing tools and show that we can encode the same analysis inside Sizzle. Those tools being RacerD and the deadlock detection tool at Meta. But I can still answer your question in the context of those tools. The two tools that I talked about, the scalable tools, RacerD and the deadlock detection tools, they assume that all conditions in a program are non-deterministic. So as a result, they don't do any branching analysis. Now, one of the things that together with people at Meta we're looking at is exactly what you mentioned, looking into. So for instance, one thing you can do is optimistically ignore the condition, assume that that path is feasible, go ahead, see if you detect the race. And when you have found the potential race, then, but we record the condition, right? Then you can backtrack and see if that condition was actually feasible or not. So that's one of the future avenues that we're looking at in terms of analysis tools. There are other possibilities based on the Sizzle theory for data-dependent bugs. And again, we're looking at them for different approaches, but it's too premature at this stage to talk about them. Hopefully that answers your question. I can't hear anything.
Another question from the audience.
Thank you for the talk. I was curious with data dependence, and maybe the answer is just this doesn't apply in the situation. If you have what appears to be a race because you have conflicting writes, but you're actually just writing the same thing, and so it ends up not mattering. Is that scenario, as well, thinking about it in terms of, if that isn't actually a bug, but it's flagged as a bug in this, what does that mean as far as the idea of finding definite bugs, similar to the last question?
So actually, your question could also be posed in the context of data agnosticism as well. So the question is, when you have two conflicting accesses that write the same value, sorry, I hear an echo of myself. It's quite frustrating, but never mind. So if I have two writes that write the same value, should I really consider that a race? Well, according to the standard definition of a data race, yes. you should at least warn the programmer that, because it shouldn't be because they're writing the same value that it's not a race. The standard definition says you should at least warn the programmer that there is a potential race, because they can try to write the same value to the same location. But there are works in the theoretical directions that classify different kinds of races. So there are works that weaken the definition data race, and exactly the scenario that they said, actually, it doesn't matter if they're writing the same value, because from an outsider perspective, really the behaviors are the same, regardless of who wins the race and writes the value, then we shouldn't consider that a data race. So here we were only working with the standard definition of data race, but given the formalism that I just showed you, it won't be at all difficult to weaken that definition to add an extra condition to say that the values written were different, but not different. Hopefully that convinces you.
All right, thank you. And that question was from Gilbert. So just to follow up, and the previous question was from Joshua Turcotti. So that's those two questions. And if there's no more questions,
I can see one in the Q&A.
Oh, there's one online. Can you put that up for us? So the question here is, can you say a little more about what it means to instantiate the framework for analysis? I'm especially curious about the deadlock instantiation.
Right. So you can, if you're familiar with the views framework, the instantiation is identical. It means that you supply a bunch of parameters to the framework. And in fact, it's very much how you do things in Iris. So we didn't go the Iris way because we wanted to get down to the brass tacks and just get the most, not basic, but at least wanted to see the focus on the most important part, which is having this generality and not really worry about things like higher order reasoning just yet. But since this question is from Tej, and I know that he's familiar with the Iris framework, you can very much think of it as instantiating Iris for a particular scenario, which means that you supply it with the PCM, you supply it with your atomic axioms, you supply it with the semantics of those atomic operations, and you prove the soundness of these atomic operations, and that's it, really. But the rest is taken care of by the framework, by the Sizzle framework.
All right, well, let's thank the speaker. Thank you so much.
Thank you.